Voyager hit a 50,000 wall at the edge of the solar system. And the thing that melts isn't the spacecraft, it's your intuition. At the moment, the boundary change showed up in its data. Earth only learned about it roughly 17 hours later. Because Voyager was more than 120 AU away, about 17,000 once, 744 kilometers. NASA JPL Voyager, Stone et al., 2013. If you hear 50,000 degrees, you picture a furnace that vaporizes metal. But Voyager kept transmitting, so either physics broke or we're misunderstanding what that number means. Here's where it gets crazy. The solar system doesn't end with a line. It ends with stacked zones: termination shock, heliosheath, heliopause, interstellar space, like invisible weather fronts layered on top of each other. Stone et al., 2005. Stone et al., 2008. Stone et al., 2013. And the wall isn't a glowing brick barrier. It's a region of plasma physics that behaves nothing like heat on Earth. The normal story starts at the sun. The sun constantly blows out a stream of charged particles called the solar wind. That wind drags the sun's magnetic field outward, inflating a vast bubble around the planets called the heliosphere, a kind of long-range space weather shield. Far away, the solar wind finally runs into the interstellar medium, the thin gas and magnetic field between stars. When a flowing plasma meets resistance, it doesn't stop neatly. It forms boundaries. First, the termination shock, where the solar wind goes from supersonic to slower and hotter, like a sonic boom made of plasma. Voyager 1 reached it in 2004 and Voyager 2 in 2007. Stone et al., 2005, Stone et al., 2008. Already, something weird. They hit it at different distances, meaning the sun's bubble isn't symmetric. It's squashed. Beyond that is the heliosheath, a turbulent region where the slowed solar wind churns and mixes, and where the galaxy starts pushing back. Then comes the real border, the heliopause, where the sun's particles drop away and interstellar particles dominate. Voyager 1 crossed that boundary in August 2012, confirmed and announced in 2013, and that's the moment the 50K wall idea latched onto the public imagination. Stone et al., 2013. This is where things get strange. Because the crossing wasn't a clean, cinematic welcome to interstellar space sign, Voyager 1 saw what you'd expect in the particle data. Solar origin energetic particles crashed, and galactic cosmic rays surged, as if a door to the galaxy opened. Stone et al., 2013. But the magnetic field behavior didn't do the simple textbook flip many models predicted right at that moment. Debate erupted, and then the cliffhanger that should have killed the story. Voyager 1's main plasma instrument had failed long before. The tool you'd want most to prove where you are was gone. You might be thinking, so they can't prove it. Stay with me, because this is where the science turns into a forensic investigation. Scientists proved Voyager's crossing using 3 clues. Count them down. 3. The heliosphere's own energetic particles dropped sharply. 2. Galactic cosmic rays rose and stayed high. 1. The surrounding plasma density jumped to interstellar values. Stone et al., 2013. And clue number 1 is the genius move. Don Gurnett's team used Voyager 1's plasma wave subsystem, which can detect plasma oscillations, ringing in the surrounding medium. When shock waves from solar eruptions traveled outward and reached Voyager, they made the plasma ring at characteristic frequencies that reveal density. It's like tapping a wall and knowing what's behind it by the sound. The inferred density matched interstellar plasma. Case closed. Voyager had crossed the heliopause and entered interstellar space. Gurnett et al., 2013. Now we can finally defuse the headline trap. The 50,000-degree wall. Here's the reality-breaking part. Temperature in space often means how energetic are the particles, not how much heat gets dumped into a spacecraft. Heating requires collisions, tons of particles slamming into you and transferring energy. Near the heliopause, the plasma density is unbelievably low. So even if the particles that exist are extremely energetic, often described in popular summaries as temperatures of tens of thousands of Kelvin, depending on region and particle population, there are so few of them that the total heat transfer is tiny. Analogy: an oven burns you because you're surrounded by trillions of molecules constantly hitting you. The solar boundary is more like a near-empty room containing only a few ultra-fast ping-pong balls. The temperature number can be huge, but the heating is almost nothing because there's almost nothing to carry energy into the spacecraft. That's why Voyager doesn't melt. What melts is the myth that temperature automatically equals burning. And that exposes the bigger discovery. The heliosphere is a massive space shield. Not perfect, because at the boundary, the shielding weakens, and more galactic cosmic rays can reach inward, but real enough that you can see it in the data as Voyager crossed from sun-dominated to galaxy-dominated. Just when you think the story is settled, the second twist hits. Voyager 2. In November 2018, Voyager 2 crossed the heliopause too, and unlike Voyager 1, it still had working plasma measurements, letting scientists directly observe the solar wind fading towards zero at the boundary. Stone et al., 2019, Nature Astronomy, 2019. That confirmed the crossing with a different instrument set. But Voyager 2 crossed at a different distance, and the transition behaved differently. The heliosphere isn't a fixed fence. It's a living boundary shaped by the interstellar magnetic field, and changing with the sun's 11-year cycle. It dents. It shifts. It breathes. Then comes the controversy layer. For years, many expected a classic bow shock at the heliosphere's nose as the sun moves through interstellar space. But IBEX results suggested we might not have a strong, clean bow shock in the simple sense, maybe more like a gentler bow wave depending on local conditions. McComas et al., 2012. So the wall may actually be overlapping effects. Hot heliosheath plasma after the termination shock, magnetic draping that controls particle access, and neutral atom interactions via charge exchange. Different directions and different solar conditions could make the barrier look different, because it is different. So I'll put it to you. I genuinely want to know what you think the 50K wall mostly refers to. A. Hot heliosheath plasma. B. A magnetic barrier controlling particles. Or C. Neutral atom sides, charge exchange effects, near the boundary. And what measurement would convince you? Because this affects all of us. The heliosphere helps modulate cosmic rays reaching the inner solar system. Radiation that matters for astronaut health, future Mars missions, and spacecraft electronics. It also connects to exoplanets. Stars with winds likely carve their own astrospheres, and a stronger or weaker bubble changes how much high-energy radiation reaches planets. One more piece of the habitability puzzle. The hopeful part is, Voyager is still out there, still transmitting with fading power, still turning guesses into measurements from a place no human-built object had reached before. And the next generation is lining up. IMAP will image the heliosphere using energetic neutral atoms, and interstellar probe concepts aim to sample the boundary in multiple directions, not just two needle paths. Voyager didn't melt at a 50,000-degree wall. It melted the assumption that space works like Earth, and it exposed the solar system's outermost shield as a real, measurable structure. And that is the kind of discovery that doesn't just change what we know. It changes how we think.